Welcome to the Explainer. You ever wonder how we know how old something really is? It's not magic, not at all. It turns out the universe has this built-in clock, ticking away right inside the heart of atoms. Today, we are going to uncover how these tiny transformations don't just tell time, they literally power our world.
So you see an artifact like this ancient manuscript, and you're told with absolute certainty that it's thousands of years old. But just think about that for a second. How do we know? It's not like there's a date stamp printed on it from way back when.
Well, the answer isn't some secret code in the ink or on the parchment itself. It's a clock. A natural microscopic clock that's been ticking away inside the very atoms that make up the object since the day it was created.
Right, so this atomic clock, it's all driven by a phenomenon we call radioactivity. Let's break down exactly how this fundamental process actually works. At its very core, radioactivity is all about one thing: stability. See, some atoms are just inherently unstable, and because of that, they will naturally change or decay to reach a more stable state. And here's the best part: they do this at a remarkably predictable rate. But why? Why are some atoms unstable to begin with? What makes one atomic nucleus totally content for billions of years, while another one is just destined to change? The secret, it turns out, is in its subatomic recipe. It all comes down to something called isotopes. Let's take carbon, for example. Every single carbon atom has 6 protons. That's what makes it carbon. But some have 6 neutrons, which makes them stable, carbon-12. Others have 8 neutrons, and that makes them unstable, radioactive, carbon-14. It's that delicate balance of protons and neutrons in the nucleus that really decides its fate. Now, what makes this whole decay process so useful as a clock are its very strict rules. You can't speed it up, you can't slow it down, it's completely unaffected by stuff like temperature or pressure. For any one single atom, the decay is random, yeah, but it always moves towards stability and it always releases energy. That makes the whole process both unstoppable and, crucially, measurable.
Okay, so let's get into the nitty-gritty of how these atoms transform. It isn't just some vague change. It's a super precise process of shedding particles and becoming something else entirely.
So first up is alpha decay. You can think of this one as for the real heavyweights of the periodic table. The unstable nucleus literally just spits out a particle that has 2 protons and 2 neutrons, which, hey, that's a helium nucleus. And as you can see from the equation, because the original atom, X, loses those particles, it transforms into a completely new and lighter element, Y.
Now, I know this slide looks a little complex, but it shows this exact process in action. We're looking at what's called a decay chain, and it starts with unstable polonium. It shoots out an alpha particle, turning into an isotope of lead. But that new atom might also be unstable, so it decays again. And this whole thing just continues until it finally lands on a stable form. In this case, that's lead-206.
Next, we've got beta decay. This is like a more subtle kind of alchemy. Inside the nucleus, a neutron just decides to flip its identity and becomes a proton. Then, to kind of balance the electrical books, it ejects a high-energy electron. The equation shows us that the atom's total mass barely changes at all, but because it gained a proton, it's now become the very next element on the periodic table.
So here's the crucial point. This is exactly what happens with carbon-14. With its 6 protons and 8 neutrons, it's just not stable. It undergoes beta decay. A neutron becomes a proton, and voila, it's now nitrogen-14, with 7 protons and 7 neutrons. Perfectly stable. This right here, this is the heart of our atomic clock.
Okay, but wait. If the decay of any single atom is random, how in the world can we use it as a reliable clock? Well, the secret is in the power of large numbers. The key concept here is what we call the half-life. While we can't tell you when one specific atom is going to decay, if you have a sample with billions of them, we know with incredible precision how long it'll take for exactly half of them to transform.
This graph shows the idea perfectly. It's a decay curve for polonium. And notice, it's not a straight line, right? It's an exponential curve. And that's because the rate of decay actually slows down as there are fewer and fewer radioactive atoms left to transform.
We can actually use this graph to find the half-life. It's pretty cool. So you start at the initial amount of polonium on the vertical axis, right? Find the halfway point, then trace it over to the curve, and then just drop straight down to the horizontal time axis. For polonium-210, that lands you at about 138 days. Every 138 days, half of whatever's left is just gone. Now for carbon-14, that exact same process takes 5,730 years. So if we go back to that manuscript from earlier and we find it has exactly half the carbon-14 of a living organism, we know one half-life is past. It is 5,730 years old. It is just that elegant. But using this atomic clock to read the past, that's really just the beginning. This fundamental principle of nuclear transformation has applications that are shaping our present and our future.
This slide really shows the incredible range we're talking about. On one hand, you have carbon-14's slow, steady decay helping us date history. But then on the other, you have a medical treatment called Lutathera. It uses the super-fast decay of an isotope called lutetium-177. Its half-life is just under a week, to deliver targeted radiation that destroys cancer cells from the inside. It's the same principle, just on a totally different timescale for a completely different purpose. Amazing.
We can also kind of force the issue. Instead of just waiting around for an atom to decay, we can trigger a transformation. By hitting a heavy, unstable nucleus, like uranium-235 with a neutron, it doesn't just decay, it shatters. This is fission, and it releases an immense amount of energy and, crucially, more neutrons. And those neutrons can then go split other atoms, creating the chain reaction that powers nuclear energy.
Now, if we look up to the stars, we see the universe doing the exact opposite: nuclear fusion. Instead of splitting heavy atoms apart, the crazy heat and pressure in the sun's core slam light hydrogen atoms together to create helium. This process of combining atoms, fusion, it releases even more energy than fission. It's the engine that lights up the entire cosmos.
So when you really step back and look at it, you realize that this constant drive for stability, this whole process of radioactive decay and nuclear transformation, it is woven into the very fabric of the cosmos. It works on every single scale, from dating one piece of parchment to powering entire galaxies.
This fundamental force of nature has unlocked the secrets of our past and given us incredible power for our present. And that just leaves one final, tantalizing question. What else is waiting to be discovered inside the unstable heart of the atom?